Hi everyone! Today let's talk about session 12.7, tangent planes, linear approximations, and their gradients. So let's do some warm-up exercise. Consider the line y equals mx plus b. Then this is the slope-intercept form. M is the slope and b is the y-intercept. So it means here this is b, okay, that's the y-intercept. And for the slope, we know slope equals rise over run, okay, so m equals rise over run. That's the slope. Suppose we want to find a vector v parallel to this line with the x component equals 1. Okay, so the x component is 1. 1 is like the run. Okay, so rise over run, 1 is 1, equals to the slope m. Then rise will equals to m, right? So the x component of the vector equals 1. The y component of the vector equals m. Okay, so this is the vector parallel to this line. Alright, and then next, consider this curve y equals f of x in the xy plane. Let's find a vector tangent to this curve at the points a, f of a, with the x component equals 1. So this is like in Calculus 1. Right? We know what is the slope of the tangent line? So slope of the tangent line equals the derivative evaluated at that point A, right? So compared to our last picture, this is like the m, right? So the x component of v, okay, the vector parallel to the tangent line, okay, we have the run as 1, and then the rise is m, but m is f prime of a. Then what is the vector v? Well, that is 1 and f prime of a. Okay, so this is the v, the vector v. So far so good, everybody? Okay. And if you can think about, there's another way to think about it. You can think of a parametrization. Okay, so because y is equals f of x, we can have the natural parametrization x is t, y is f of t. Well then, the tangent vector is the derivative of the displacement, that equals 1, and then that is f prime of t, right? And when we plug in a at the point when, so because x equals t, right? When x equals a, that corresponds to t equals to a, so that is 1 f prime of a. You see, our answer agrees. Okay, so that is in the two-dimensional xy plane. Okay, what happens if we have in the space? Then we have z is a function of x and y, so two variables, two independent variables and one dependent variables. So let's find the vector v tangent to this surface at the point a, b, f of AB, with the x component equals 1 and the y component equals 0. Okay, what does that mean? Well, in this case, because the y component is 0, we can assume that we are on the plane that is, the y is fixed. Okay, so here y is fixed. Okay, and then we can intersect with the plane. So intersect with the plane like y equals b. Okay, so this point is AB. Alright, so when we intersect it, then we get a curve. Okay, so we get this curve. This is a curve when we intersect the surface with the plane y equals b, right? And this curve has a tangent line, right? Okay, so we want to find a vector v that is in the direction of this tangent line. So v is right here. Okay, so this is v. So we want to have the x component equals 1, and then the y component is 0. Then what is the z component? Well, this is actually partial x at the point a, b, right? Because we suppose y is fixed and we let x varies. So this is partial f, partial x. Then what is the vector v? Well, that's going to be x is 1, y component is 0, and the z, okay, that's partial f, partial x, evaluate at a, b. So far, so good, everybody? Okay, how about the next picture? Well, the next picture, we want to find a vector that's tangent to the surface at the point with x components equals 0. That means x is fixed. Okay, y varies. So we want to intersect with the plane. Okay, so intersect with the plane x equals a, because this point is a, b, right? X is a, or y equals b. Okay, then we can see this plane intersect the surface and we get a curve. So, and then we want to find a tangent line of this curve. Okay, and furthermore, we want to find the direction of this line. Okay, so v, let me draw it more straight. So this is the v. Okay, so we want to have the x component is 0, the y component is 1. Then what is the z component? Like the previous example, because we consider z is a function of y, with x is a fixed constant, right? So this is partial f, partial y at the points a, b. So that's why our v, x component is 0, y component is 1, z component is partial f, partial y at the points a, b. So far, so good? So this is the picture. How do we get the tangent vector that is perpendicular to the y-axis and or tangent vector in the x direction and the y direction. So far, so good, everybody? Okay, let's continue. In the previous sessions, we discussed how partial derivatives with respect to x and with respect to y measures the slope of the two lines that are tangent to the graph at the point. Okay, then tangent plane to the graph at the points is defined to be the plane containing those two lines. So let's draw our picture again. We have this line, this plane intersects, and we get this tangent line, right? And we also have this plane intersect, get this curve, and then we get a tangent line over there. And those two lines, okay, those two lines can give us a plane, okay? And this is the tangent plane. To find a formula for the tangent plane, we will first find two vectors that are tangent to the surface. And we already did, right? So, and then when we take cross products of those two vectors, we can get a vector that's normal to the tangent plane. Okay, that's what we need for a plane equation. We need a point on the plane, okay? And we also need a normal vector to the plane. So, what is the vector tangent to the surface and perpendicular to the y-axis? Okay, so perpendicular to the y-axis, I mean that like with the y is fixed, okay, I mean the y is fixed and x varies. Well, x varies, then we have, let's say u, because y is fixed, so the y coordinate is 0, so x varies, so we have 1, and then this is partial f partial x, okay, because x is the variable at the point AB. And then next, the vector tangent to the surface and perpendicular to the x-axis. Okay, in this case, because it's perpendicular to the x-axis, then the x is fixed. Okay, and then the y varies. So let's call it v, because x is fixed, let it be 0, and then y varies, so let it be 1. Then this is partial f partial y at AB. Okay, and then how do we find a vector normal to the tangent plane? Well, we have two vectors. Now we can consider the cross products of it. So cross product, remember the first row, I, j, k. And then the second row is the first vector. And to simplify notation, let me just put fx and fy, okay? So that is I, and then let's look at the minor, which is the determinant of the submatrix 0, 1, fx, fy, and then minus j, right? And then we have the submatrix 1, 0, fx, fy, and then plus k. We have the submatrix this guy, right? So 1, 0, 0, 1. So that is I. Okay, cross multiply is 0 times fy is 0 minus 1 times fx. Minus j, 1 times fy is fy, and then minus 0 times fx is 0. K, 1 times 1 is 1, minus 0 times 0 is 0. So what do we get? We get minus fx, okay, of AB, minus fy of AB, and then the last coordinate is 1. So far, so good, everybody? Okay, now we know the points on the tangent plane, okay, and then we also know the normal vector, okay, so this is the normal vector. Then we can construct the plane equation. How? So we use the first coordinate of the normal vector times x minus the first coordinate of the point, and then plus second coordinate of the normal vector times y minus second coordinate of the plane plus 1, which is the third coordinate of the normal vector, and then z minus f of AB. So this guy equals 0. So far, so good, everybody? Okay, then what do we get? Well, let's keep the z on the left hand side and move all the terms to the right. Then we have z, because we move all these terms to the right hand side, we get positive fx AB. Let me put f of AB first. Then partial x of AB, x minus a, partial f partial y, AB times y minus b. Okay, so this is the tangent plane equation. Yeah, so formula 1 for the tangent plane to the function z equals f of xy at the point AB, f of AB, is z equals f of AB plus partial x of AB times x minus a plus partial f partial y AB times y minus b. Do you still remember from Calculus 1 what is the tangent line equation? Okay, so in Calculus 1, What is the tangent line at the point A, f of A? Well, that is L of x equals f of, or at that time we use y equals f of a plus f prime of a x minus a, right? This is a tangent line equation. And right now it's very similar, right? Because z is now a function of x and y, so we have z on the left. And then the function value at that point, so f of ab plus the derivative times a linear factor in x and in y, okay? So that's the derivative times the linear factor. But because z is a function of two variables, so you need to have another derivative and the linear factor in y. Okay, so it's still very similar. So it's like we generalize the idea from Cal 1 now to Cal 3. Okay. All right. So, and then let's look at the following example. So let's f of xy equals this function. Find the Cartesian equation for the tangent plane to the graph at the point. Okay, let's see. So what is f of 2, 1? We plug in x is 2, 2 squared is 4, y is 1, y is 1, so 1 cubed is 1. 3 times 4 is 12, minus 2 is 10. Okay, so this is the function value at that point. And then we need to find the partial derivative. Partial f, partial x equals, we consider x is the variable, and then y is just like a constant. So 2 times 3 is 6xy. And then 2y cubed has no x in it. So that is like a constant, right? Derivative of constant is 0. And then how about partial f, partial y? We consider y is the variable and x is the constant. Derivative of y equals 1. So we have the constant multiple and multiply by 1 minus derivative of y cubed is 3y squared. But 2 times 3 is 6y squared. Is that okay, everybody? Now let's plug in the points. So we have x is 2, y is 1. This gives us 12. X is 2, y is 1. That gives us 3x. 2 squared is 4. 6 times 1 squared is just 1. Wow, that's 12 minus 6 is 6. Okay, now we're ready to plug into the equation. F equals f of 2, 1, which is 10, plus fx, okay, which is 12 times x minus a is 2, plus partial f, partial y, which is 6, and then y minus, okay, the point is 1. So far, so good. Let's simplify it. Distribute it. 12x minus 24. 6y minus 6. So z equals 12x, 6y. And what is the constant term? 10 minus 30 is negative 20. So far, so good, everybody? Okay, so right now I want to show you some picture. So let's look at this. Okay, so this is actually our second GeoGebra project. Okay, I give you instruction and you can watch my YouTube video to construct this surface. Okay, so the red is the surface. And then you can see the red axis is the x-axis. The green one is the y-axis. And the blue one is the z-axis. And then you can see the vector u. The vector u is, we have the y-coordinate is fixed. And then we have the x varies. And that's the tangent vector like in the x direction. okay? Or we can think about it's like perpendicular to the y-axis. Not quite exactly. I think it's better to just say y is fixed and then x varies. So the tangent vector v, okay, is with the x is fixed and the y varies, okay? And then you can see this light blue is the normal vector, okay, when we compute the cross product of it. And then that will give us a tangent plane. So this purple plane is the tangent plane. Okay, so can you imagine? So we can also let the x, the point A to move. You can see how it change. You can see how it change. Yes. We can also let the y move as well. Okay, so now x and y, A and B, the points is moving. Then you can see at each point, how would the tangent vectors u and v and the normal vector changes. And you can see the tangent plane changes as well. Isn't it very cool? So I hope that this animation pictures can help you understand what is happening in this space. Okay. So don't forget to do your extra credit projects. Okay, let's come back. Okay, let's continue. Linear approximations. In Calculus 1, I hope you learned how to use derivative to approximate functions using tangent lines. This is an important idea called linear approximation. And when we zoom in toward a point on the graph of a differentiable function, the curve becomes arbitrarily distinguishable from its tangent line, and we can approximate the functions by a tangent, by a linear equation, the tangent line. Okay, so this is from Calculus 1. You can see when the point is, so this is A, right? And when the point X is getting closer to A, you can see the line, the tangent line and the curve, they're very close to each other, okay? And this method can help us a lot because the tangent line only use operation plus, minus, multiplied, and subtract. Very simple. So, and if we have some crazy function like square roots, natural log, exponential function, sine, cosine, and you don't have a calculator, what do? You can use this linear approximation method and you can get a very good approximation. And the operation you use is only for basic operation plus, minus, multiply, and divide. Okay, so all right. So let's see. Tangent line at a f of a. So we know Lx equals f of a plus f prime of a x minus a. This is the tangent line, right? And actually in Calculus 2, I hope you still remember the tangent polynomial. Okay, so the tangent polynomial is also, we can use tangent polynomial to approximate a given function. So when we increase the degree of the polynomial, we actually get a better and better approximation. So it's not only tangent line, we can use quadratic or cubic, or we can use any tangent polynomial with degree n to approximate it. Okay? Alright, so as long as x is very close to a, the tangent line at x equals a is very close to the graph of y equals f of x. Okay, so this is from Cal 1 and Cal 2. Now, we're in Cal 3 and we're talking about surfaces. Okay, then instead of using tangent line to approximate curve, we can use tangent plane to approximate surface. Okay, the idea is the same as before. As we zoom in toward a point on the surface, that is the graph of a differentiable function in two variables. The surface becomes particularly indistinguishable from its tangent plane, and we can then approximate the functions by a linear function. Okay, that which is the tangent plane. Can you see the picture right here? So linear approximation, so if the point xy is very close to the point AB, then f of xy, so this is the function, is approximated by this guy is the tangent plane. Okay, and we know tangent plane is f of AB plus partial f partial x times x minus a plus partial f partial y evaluate at AB times y minus b. Okay, keep in mind these two, they are numbers. Okay, it's not functions. You take partial f partial x and partial f partial y, then you plug in the numbers, the points a b, so you can get numbers. So that's why this guy is a linear equation in two variables, or this is a linear function in two variables. Okay, but it's still linear. All right, let's continue. So here we have a function. So part A, find the tangent line to the graph at the point 2, 0, f of 2, 0. Okay, so let's do it. First, what is f of 2, 0? So we plug in x is 2, y is 0. Well, 3y squared is 0, e to the 0 is 1. So we have minus 4 plus 1 equals minus 3. So far, so good, everybody? And then we want to find partial f partial x. That equals, we suppose the y is constant. We want to take the derivative with respect to x. So we have minus 2. And then 3y squared is just going to be 0. The derivative of it is 0. And then e to the xy, this is chain rule. E to the u is e to the u times u prime. But xy prime, we're taking the derivative with respect to x. So the derivative of x is 1, but the constant multiple y stay there. Okay, so this is the partial f partial x, and partial f partial y equals derivative of negative 2x is 0, 3y squared, the derivative is 2 times 3 is 6y. Here, chain rule, e to the xy, but xy prime, we're looking for the derivative of respect to y. So derivative of y is 1, then we have the constant multiple x. Okay, then what is fx? Evaluate at 2, 0. Well, we plug in, so because y is 0, ooh, that's nice. E to 0 times 0, so we just get negative 2. And then fy evaluate at 2, 0. 6 times 0 is 0. And then here, e to the 0 is 1. 1 times x is 2. So the answer is 2. Well then, what is the tangent plane? So the tangent plane z equals, what is that? Oh, we can also say is out of xy is a tangent plane. It's a linear function in xy. Okay, so that equals f of 2, 0, negative 3 plus partial f partial x evaluate at the point negative 2, x minus the x coordinate of the point. Okay. And then we have the partial f partial y, y minus the y coordinate of the point. Okay, so that's negative 3 minus 2x distributes. Minus 2 times minus 2 is plus 4, and that's 2y. So we have negative 2x plus 2y minus 3 plus 4 is plus 1. Do you have the same answer? So remember when we go over each example, I hope you can pause the video at the beginning and then continue to work on the problem, and after you're done, you can check your answers, okay? So in this way, you can practice. So part B, estimate the value 2.1, f of 2.1 and negative 0.05. So notice that 2.1 is very close to 2. Negative 0.05 is very close to 0. So whenever we want to use this linear approximation, the points we're looking for it must be very close to the points that we get the tangent plane. Okay, so let's use that. So f of 2.1 minus 0.05 is approximated by the tangent plane. It evaluates at 2.1 and negative 0.05. That's minus 2x, x is 2.1, plus 2y, y is negative 0.05, plus 1. And what is that? Okay, let's plug into our calculator. So we get negative 2 times 2.1 minus 2 times 0.05 plus 1. The answer is negative 3.3. Okay, so far so good, everybody. So you can see we can calculate it by hand, right? We don't need a fancy calculator. In fact, we can calculate by hand, right? And well, that's awesome because look at this guy, e to the xy, right? If you want to put this number into our function, we have to use a calculator. But now, without a calculator, we can get a number is quite close. Is it really close to the actual value? Let's check, okay? This is the nice thing of this kind of problem because we can always check whether our answer is close to the true value. If it's not, then maybe we make some mistake. So let's use our calculator. So this is from the calculator. We plug in directly. So let me see. Negative 2 times x is 2.1 plus 3 times squared, then 0.05 squared. And then plus e to the, so 2.1 times negative 0.05. Okay, so my answer, you can also plug in your calculator and see whether we have the same answer. I get negative 3.292175477. Are they close? Yes. That means, very good. So far, so good. Yeah, so when you see this kind of problem in the exam, after you're done, you can plug in evaluate the functions and put the numbers in your calculator. If the answer is close, then you're good. So far, so good, everybody? All right, so let's continue in video part B. See you soon.